Okay, so today we're going to be talking about increasing, decreasing, and the first derivative test. So we know that a function can be doing any of three things. It can be increasing, it can be decreasing, or it can be staying constant. All right, so it can go up, it can go down, or it can just hover at the same value. So we're going to be looking at how to interpret different things. And the way that we could do that is by analyzing the slope or derivative function. All right, if you take a look at this first graph, this function is increasing. And if you analyze the derivative, okay, or the slope is positive everywhere. All right, this function's decreasing, the slope is negative. And this function is constant, the slope is 0, okay? So we're going to be looking at how these two, the function and the derivative, are related. So to determine whether a function is increasing, you just have to figure out where the derivative is positive. To figure out where it's decreasing, the derivative's negative. And to figure out where it's constant, the derivative is 0. All right, and this is something we have already talked about. If the derivative is always positive, the function's always increasing. Okay, so if you analyze something like x cubed, if you take that derivative, the derivative is 3x squared. And so our actual function, if we draw f, that's x cubed. It's always increasing, and that's because the derivative is always positive. All right, so moving on to example 1 here. We have the graph of a function defined on -3 to 5. We're trying to list the open intervals over which the function's increasing, decreasing, or constant. So it looks like the function is increasing from here to here. All right, so we could say it's increasing from -3 all the way up into 1. It's constant between 1 and 3, and it's decreasing from 3 to 5. Okay, so if we look at the derivative is positive for all of these. It's 0 here, and it's negative for all of these. And the reason why we use open intervals, because if you look exactly at that point 1, can you tell if it's increasing or if it's constant? Is the slope right there, is it positive or is it 0? All right, so you have to be very careful with those points, and the way we avoid any problems is just to use open intervals. There are only a few points where a function can change, increasing, decreasing, and constant. Continuous functions can only change at critical values, whereas a discontinuous function can change at critical points or at discontinuities. So here we have a little tiny bug crawling up this function. All right, if the ant is walking uphill, the function's increasing. All right, so we're going to list the open intervals over which it's increasing. So that would be from -infinity all the way up to 1, 2, 3, 4, 5, -5. And it looks like it's also increasing from -5 to 0. So even though -5 isn't a critical value, it is a discontinuity. So we can change increasing, decreasing, or constant at those values. In this case, we didn't happen to. All right, we have this critical value where the derivative is 0. So from 0 to 5, it's decreasing, and also from 5 to infinity. Oh, wrong way. All right, so without the graph, we have to analyze the algebraic representation of the function. All right, so if we're looking at this function here, we're going to try to figure out where the derivative is positive or where the derivative is negative or 0. All right, so we take the derivative, it's 3x squared minus 3x. If we look at where, that's never undefined, so it's always defined. If we figure out where it's equal to 0 at, all right, it's a simple factoring problem. Factor out a 3x, you get, x minus 1. So we have two critical values, x equals 0 and x equals 1. So one thing that we can do now is analyze our function. If we look at, put the x values here and the derivative values here. All right, x is 0. Actually, whoops. Let's do it this way. X is 0, x is 1. So if we pick some different numbers in between those, so maybe if we pick like 1/2, 2, and -1, all right, you can see what's happening. Plug it back into the derivative function. If you plug in -1, you'll get a negative times a negative, which ends up being positive. All right, if you plug in 1/2, you get a positive times a negative, which is a negative. And if you do 2, you get a positive and a positive, which gives us positive. So now this tells us where our function is increasing, decreasing, constant, where it has relative mins and maxes. So if the slope is positive here, your function's increasing. All right, so it's increasing, then it hits 0, it starts decreasing, and then it hits 2 and it increases again. So maybe it looks something like this. All right, and those are the intervals, increasing from -infinity all the way up until 0, decreasing from 0 to 1, and then increasing again from 2 to infinity. All right, so if our function's increasing and then it changes to decreasing, what we're going to be looking at soon is there has to be a relative maximum there. And if it's changing from decreasing to increasing, there's got to be a relative minimum value there. And we'll get into that. But first, just practice with this. So find the intervals on which this is increasing or decreasing. This shouldn't be too tough of a problem. I'd like you to try this, okay? And I'd like you to put your answer in the whisk. Just tell me the intervals on which it's increasing and decreasing, because it's not going to be a constant function. All right, so what I kind of introduced there is the first derivative test. Okay, this gives us a test for relative extrema. As I showed, and you can read that on your own time. Whoops. As I showed, if your function is increasing and then decreasing, if your derivative is positive and then the derivative's negative, there has to be a relative maximum there. Whoops. Okay, at x equals c in this case. If your derivative's negative and it changes to positive, there has to be a relative minimum there. Okay, if the derivative doesn't change signs, if it goes from positive to 0 to positive, then there isn't a maximum or minimum there. All right, we'll talk more about what that's going to be later. This is really important. It's in bold and there's stars, okay? It's extremely important. When you're using the first derivative test, all right, so let me go back up here so I could talk about it. We would say that there is a relative, we could say f has a relative maximum at x equals c since f prime changes from positive to negative at x equals c. This is how we're going to have to, if we want to use the first derivative test, this is what you're going to have to do to explain that. Oh, come on. You have to say f, or you have to say the derivative. All right, the things that you shouldn't use if you're going to say it. The graph. Which graph? Are you talking about f? Are you talking about f prime, f double prime, g? I don't know which graph you're talking about. You also shouldn't say the function, because all of those things are functions, so I don't know which one you're talking about. And worst of all, you should never say it, because then we have no idea what you're talking about. Are you talking about an x value, a y value, a point, a number? Okay, so you have to be very specific with this. Let's see. So this is something that we could do here. Find the x-coordinates of the local extrema on this. So local extrema, remember, are going to happen at the critical value. So we should find the derivative. So we're going to get 1/2 minus cosine of x. And remember, this is always defined, so we don't have to check where it's undefined. But we should look at where the derivative is 0. And that's going to occur when cosine is 1/2. And if we look in our domain, we're looking from 0 to 2 pi. So there should be 2 places where cosine's 1/2. If you know your different values, you could see that it would be at 1/3 pi and also 5/3 pi. All right, so we need to use our little chart for our first derivative test. So we have our one critical value here. We have another critical value here. Okay, we want to pick some points in between them. So a good one on our interval would be 0, maybe pi, and we could also say 2 pi. Plug in those values and just see if they're positive or negative. Okay, in this case, it's going to be negative, positive, negative. From that, we can say where the local extrema are. Okay, if our derivative's going from negative to positive, our function's going from decreasing to increasing, so there has to be a relative minimum there. So that's what we write. All right, since f prime, or the derivative, changes from negative to positive, and you have to write this out every single time. All right, negative to positive at, I guess we should say where, at x equals 1/3 pi. Cross that out. All right, f has a relative minimum at x equals 1/3 pi. Okay, similarly, we have this, it's going from a positive slope to a negative slope, or increasing to decreasing. So since f prime changes from positive to negative at x equals 5/3 pi, f has a relative maximum at x equals 5/3 pi. If you needed to find that maximum value, all you would have to do is plug it into your function. But for right now, we're just looking at the x coordinates. We'll continue on with these examples tomorrow. All right, but for now, I want you to go ahead and start working on a few problems from this section.